Hello and welcome back to Compiler Programming. Today we're going to continue where we left off yesterday, which is trying to support more than 4 arguments to the function, and in particular that means that we will need to put them on a stack. So in the last video I had to fix up how we do stack reservation and do this patching of the stack displacement to make sure that the variables are reserved further away from the stack pointer, and the space next to stack pointer will be reserved for functions. So when we now do this function argument, we will also need to update in the builder the value that will tell us what is the maximum stack size that is reserved for a function call. Because if we look at the code, I will bring up the compiler explorer here, and if we call, for example, the function with 5 arguments and a function with 3 arguments, I expect that we will not actually allocate extra stack space. Instead, we will just reuse the stack space that we got for the bigger version, and we can verify it here. So we did allocate a bit more here, which I'm not sure exactly why. Maybe because of the intermediary values that are coming from return. Yeah, indeed. So it's just it saved the return value. But apart from that, we do not need kind of to have extra stack space for parameters, and we just check which of our calls needs the biggest stack size. So let's do it that way then. We will need to have now value h, because I believe we had to move function builder here. Indeed we did. And one thing that we will need to add now is let's scale it U32 max function stack size, I guess. Yes. And another thing that we will need is the reservation for our own. Wait a second. No. I'm just trying to figure out where do our. Okay, so home area things, they go before the stack allocation, so we don't have to worry about that. We only have to worry about the functions that we are calling. So max function or max call stack size. So that sounds about right. And when we call the function, then we will need to deal with this. Let me bookmark this so we can quickly jump to here. Okay, so this is our call. We are passing the builder, which is good. And we can see how much space we actually need. For now, I will do the simple version, I guess, of this function, this calculation, because later on we will need to have this parameter passing for bigger things. But for now, this is fine. So basically, what we say is U32 parameter stack size is 0, and then actually we can just do this argument count times size of S64. So if I understand correctly, the calling convention is described here, and in particular this paragraph that says that we never pass by value anything larger than 64 bits. Instead, they are passed by pointer. That means that it is pretty safe for us to just take the amount of arguments and multiply it by the pointer size, which is 64 bits. So we are only targeting 64-bit architecture. Okay, so this is good. And we now can say that builder max, what was it called? Max call stack size. Maybe we say, oh, this is parameter. Parameters, let's call it, let's make it consistent. Max parameters stack size, maybe even more explicit, max call parameters stack size. I like that. Max call parameters stack size is max of builder and whatever we have here, which is parameters stack size. Okay, conversion from size t to u32. Okay, whatever. I can be even hard coding here. Argument count is S64. Okay, maybe we can change that. Cool. So now we have this this stuff, and if we run tests, nothing should actually change because we are not using that yet. But one thing I wanted to do is to see sort of what will change once we start applying this value. And I guess I can do it without the debugger. In here, we have this stack size, right? And we can print it. So let's do printf %d and say that this is our stack size. We run tests and we will see basically the stack sizes for each test. This is actually not 88, it's, let me do space here so it's visible. Yeah, so these are the stack sizes, but if we are calling a function, then they are gonna increase. So because now what we're gonna do is we're gonna say that builder stack reserve is plus equals builder max call parameter stack size. Okay, let's check what it will be right now. So it was these values, and now if I run, we will have much larger ones, or apparently not, and we will also crash, which is kind of unfortunate. Let's think about why that happens. So let's not add it, but instead let's just print it and see what's going on. So I will add a comma here and slash and here. So it says 8 and 8. Okay. That's interesting. We never have more than 8, so I guess we are not calling functions that have more than one argument. But our hello world becomes pretty broken when we try to actually add this to here. Well, let's check this out and try to understand why it explodes. For that, we will need a debugger, definitely. Okay. Let's check the debugger and see what is going on. Where is our hello world? Hello. Good. Let's see what's going on. And we need to switch to disassembly and see what's happening here. So we are substituting the, okay, so this is minus 24. Then we do a call and then we add 24. All of that seems quite inconspicuous. However, let me think about this. So 24 is not 16-byte aligned. So maybe that is the issue. Move. So I guess it is the call that fails. No, I don't know where the... Okay, that's fine. So it puts it on the stack. Then I'm just wondering at which point does the thing actually explode? So this is probably counting how many characters are in the... Okay, so it actually outputs hello world without any issues. But it explodes when we are trying to return. Why does it explode when we are trying to return? A bit confused. What does it try to do here? So this is our hello world example. We call that function and then we return. Let me see that again to check where we actually fail. So call is fine, call is fine, call is fine. call. So all this is okay. And RSP 18 is fine as well. Okay. What happens if if right now I press F10, then it's gonna explode. Access violation executing location 0D. So what happens is we somehow overrode the return address of the function with something else, which is not very nice. Okay, let's see what happens if we try to do it here. So void test is puts of hello world, right? This is what we are trying to do. Oh. And let's see what happens. So interestingly enough, it reserves a big chunk, so to 40 bytes. Is it possible that it always reserves the like at least 4 if it calls a function? I mean, we can try that and see if that improves our situation. So let's see, where was it? It was call, yes. In here, we could say that we want the max of 4 or argument count. So we say at least if we are calling a function, we'll at least reserve space for 4 arguments. Let's see what that will do for us. Okay, so that is the correct thing. That definitely deserves a comment saying if we call a function, then we need to reserve space for the home area of at least 4 arguments. I'm not sure, that needs to be verified, but for now that seems to fix our issue and all the tests are passing. So that's good enough for me for now. And we can continue with what we wanted. Okay, so that's very good progress. And now we need to start implementing the actual support for this, right? So I uncomment that, I try to build it, I try to run it, and it explodes with not implemented, which is actually what we wanted to do, right? So this case. Now, the question is, how do we deal with this? Because we don't want to do directly reserve stack, because we want this function to take care of figuring out how much space we need, right? So we want to keep this calculation for parameter stack size in here. So I guess in function arg, we will duplicate at least part of the logic from reserve stack and do it manually. So let's take that thing and put that over here. Now, the first thing I'm not sure about is if we need to always reserve at least 8 bytes or not, or we actually use the size of the descriptor. My guess is we always need to reserve 8 bytes, and we can check that pretty easily. So we have this set of functions that are here, and we could check how much it will actually reserve. When we try to change, for example, the last argument to be smaller. So right now it reserves 72 bytes, and if we do this and do this, it still reserves 72 bytes. And if we look inside of the function itself, yeah, it still aligns it to 8 bytes from what I can see. Let's check what's written here. Integer first for stack, push to stack, aggregates, okay, pointer, unprototyped, return values. Return values are also interesting because they are slightly different, but what I wanted to figure out is what is about other parameters? Parameter passing. They just say pushed on the stack, but they don't really say if. So let's add one more and see what they do here. So it will be like this, and we say 6. Okay, so this is interesting. It is still so this should be RSP plus 4, if I understand correctly how this works. Or not. Arg0, arg0, arg1, arg2, arg3, arg4, arg5. So this is 72. Okay, I was looking at the wrong thing when I was checking this previously. So it looks like they are still aligned to 8 bytes. And arguments start at 20. Okay, so this is another funky thing, that we are not using frame pointer. And that means that when we figure out where the arguments are located, we will need to adjust their offsets based on our stack size. So since I also have some stack reservation in this function, I need to basically add up the offsets that are coming from the argument with this offset that is coming from here. So if I can see that, for example, argument 5 is at offset 72, and that probably comes from 24 here plus 48 because it is a sixth argument, and 6 times 8 is 48. Okay, so let's try to figure out how we're gonna deal with all of that stuff. So for the arguments, we also don't know ahead of time, like before we finish encoding the whole function, we don't know what will be the full stack size. So I guess similar to how we are dealing in here with the regular stack allocation, we will need to deal with the arguments as well. The question is, do I need to implement a special logic for this, or our current one can be used or modified to support this? Let's actually see what happens when we do this. Okay, so we are coming here and we want to look at what is argument index. So we say argument index is this. And like so. Okay, this is perfectly fine because we already did that up over here. This compiles. So we have argument index. And the higher we are going here in arguments, we see that offset grows for each of them. So it will definitely be something like, say, S32 offset is argument index times 8. But here we need to do this plus whatever is the allocation for this stuff, right? And okay, let me copy this stuff. We don't want to stack reserve actually. And here it will not be stack reserve, it will be offset. And here we say, we just do it like this. So this at least compiles, but I'm not sure what's going to happen. So for example, let's take the fifth argument, right? If the function does not need any stack, so this fifth argument will be at offset 40, and let's see what happens if we plug 40 into here. So patch will say that it will be 40, and we will take stack size and subtract the 40 from it, which is not what we want. We want to actually add to the stack size. So here we could probably cheese it and encode negative displacement into here. So say like minus argument index times 8, and we will also subtract byte size, which we again don't really want to, but we can compensate for that by saying plus byte size, or rather minus byte size. So if I'm not mistaken, if we take these and we plug it into here, we should have stack size plus what we wanted. Well, let's see what happens when we try to run this. Okay, it does not really work. The question is, does it not work for this thing? So we have third argument. Oh, what's happening here? Okay. Yeah, so this fails. Let's take a look at what fails. So we have this nice fifth argument function, which we can take a look at and see what is going on inside. Oh, so it actually explodes in a different place. It's even explodes way before we are done. What does it look like again? It is fifth argument, and we say return argument 4. I think I know what's going on. If I remember correctly, we cheesed it in the function, descriptor function, argument list, argument count. Yes. Argument list. Yeah. So this is a bit of yikes, where we need to be more supportive. So let's do it this way and try to run tests. Okay. We still fail. Do we fail in the same place? So we are still failing here. It says it tries to in location 0. Oh, yeah. I think that's actually happening because, yeah. That's not really what I want to do. What I want to do, actually we can even do it like so, to not have copy paste, but we will need to add breaks now. Okay. Break. Good. And here it also should say argument index. Let's try that again. Okay, so we didn't explode, but we didn't get the correct result either. And this is because, actually, I'm not sure why it is, so let's check it. We need to get to our fifth argument, and yes, That's a good place to break. So we are putting it at, the argument will be at RSP plus 20. And now let's see where our function expected to be. So matches these operands. Okay. Let's step inside. And it expects it to be at RSP plus 20H. 28H. But that's actually not true, because when we do a call, we also push the return address on the stack. So it will actually be RSP plus 32H. So let me check like this. Okay, is this 0? Is this what we wanted to have? No, it should be 5. Oh, let's try to figure out. We don't actually need this int, I believe. So this is interesting. Will it be 40 then? No. 20. Okay. No, this is wrong. First, I need to step over this sub. But now I am a bit confused. So value here is total bullshit. Value here is very much so as well. So I guess I want to see how RSP changes when we call the function. Okay, let's do that again. Start disassembly. Think, 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 think. Okay, and this is not very nice because we have RSP that is it like finds a variable called RSP, and this is not what we want. And I have no idea how to force it to show me the register. Okay. So I guess that is like this. So this is the value of RSP. We can kind of stash it here so we have it. And, or I can put it here. That also works. Okay. Let's, okay. I was stepped over the wrong thing. Sorry about that. We'll have to do it again. Okay. So this is our stack pointer right now. And if we jump inside of the function, then it is pointing to, yeah. So we actually, yeah, when we do the reservation, we are subtracting from the stack. So let me check that before we call, we actually have 5 in the right place. So let's do like this. Okay, ding, 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 ding. Okay, we have 5 add RSP plus 20. Let's step inside. Now we should have 5 at RSP plus 28. We do. And when we do one more, we now should have 5 at RSP plus 32. But we instead have 0. Or actually, no, it should be plus 20? No. Okay. I'm a bit confused now. So our RSP is it's I'm confused because of hexadecimal mathematics. It's always easy to just start thinking in decimal and like add 8 or add 10 and expect it to be the right thing. But yeah, so it is, I was right. We just need to add 8 to here. It will be at 0x30. Okay, let's try that out. Let me add another bookmark here. And this means that over here, we need to also account for the return address being pushed on the stack. And it's an interesting question, who should account for that? Should this thing account for that, or should the function, this function end account for that? I guess let's do it here. So for now, we will do lots of, can even do this, to return address size to make our code a bit more self-documenting. And we also need to use minus here because we want to end up adding it when our calculation happens there. Let's check this out. It still does not work. Should it then be... Let's check what is happening now. Disassembly, blah blah blah. Okay, now it does RSP minus 10. Say what? Oh yeah, because it should be minus here. I accidentally get rid of it. Great. So this is at least the correct calculation for the fifth argument. Obviously, where there is a fifth, there needs to be a sixth one. So let's just try that. I will for now change this function, and later we will also need to figure out how to improve the test setup so that we can easily test way more cases, right? Because the tests that we're having right now, they are all good and well, but they're not really covering a lot of stuff. For that, we will need way more things. Okay, some more type definitions. This is a bit of a annoying part of dealing with this with C in C, because in C++ you could, for example, do some template magic, but alas, it's not the case. So function args. Result should be 6. Okay. The result is still 6, which is great. That means we are doing well. Let's also try this version because I'm interested if our calculations will be off. Actually, I'll do it like so. So I still think that like it should still be right because we are not actually using byte size for figuring out what will be the offset of these things. Instead, we always say that it's going to be 8 bytes per argument. And it still works. Great, great, great. Let's end this. And we probably want to add another one of those volatile comments and figure out if we want to change this calculation later. Stack hatch. This relies on the algorithm used in function and to update stack locations after we know how much stack space is going to be required for function. It's going to be required for the function. Nice. This is good, and we can add another thing over here. Probably without the comment. And that way we will at least know that if we're changing this line, we should pay attention and think about checking these places for real changes as well. Cool. And now another thing that can happen is when we return a value that is bigger than 64 bits, but since the rest of our code is not really ready for that anyway, and it will require changes in a lot more places, I will tackle it separately. So I think this will be it for today. Now we support any amount of arguments essentially. So thank you very much for watching and see you next time.